Okay, hi everyone. I'm Alessandro Chiarenza. I'm a second year PhD in Palaeontology at Imperial College, and my PhD research focuses on dinosaur diversity and fossil bias associated with them, and especially I focus on late Cretaceous diversity. Also, I'm Italian, so you would forgive me for my excess of gesticulation. And so there are several ways of analyzing dinosaur diversity in deep time and ecological diversity generally. We've been seeing a few examples during this session and the past session. Disparity analysis, quite common. There are row counts, taxonomic occurrences through time, bin analysis. There are also species birth and death models to do that. And depending on the different approach and the different orders, some interpretation on the actual ecological diversity trend through times can vary quite a little bit. And these sort of different results, these different outcomes can have an impact whenever we got some topical interpretation in some particular events in times, like, as we've seen before, the late Cretaceous dinosaur diversity trends, and eventually the demise on the leading up of the KPG mass extinction. So, but how are the diversity patterns biased by, fossil bias, the rock record? So, for example, if we analyzing a diversity trend which is severely spatially biased, as we see, all dinosaur occurrences are, of course, related, like strongly correlated with terrestrial fossil outcrops in the late Cretaceous. So you're basically basing some macroecological dynamics, regional dynamics, or even global dynamics on a very strongly reduced subset of data. For example, in North America, you've got the most dinosaur outcrops are in between Kansas and Montana, and they confine to Laramida, so it's like 20% of the all continental landmass area. So, as we've seen recently in a few papers outlining that and quantifying that, there is one of the most impacting effect in masking the actual diversity of taxa in time is the spatial bias. This has been outlined and quantified by recently, 2 weeks ago, in our NETCOM paper. And so, but is this a problem that only paleontologists have stumbled on, or this is actually a problem that even actual ecology have got in the past? So there are ways, neontological way of approaching in that, especially when you need to interpolate between fragmentary and dispersed spatial data. And one of these is ecological niche modeling. Niche modeling is basically this modeling approach where you train your sets of spatial data, taxonomic occurrences, to the climatic conditions or environmental conditions corresponding to their coordinates, then building some machine learning algorithm or linear generalized model algorithm, and project that to other condition, to other area, and so you can kind of reconstruct the actual abiotic niche of a determinate taxon. And this sort of approach has been shown very powerful, especially in conservation biology, for example, to projecting diversity trends in other scenario of climate change or global warming, stuff like that. And to be clear, when I talk about ecological niche here in this talk, I'm referring to an abiotic fundamental niche in an Hutchinsonian term. So the hypervolume set of conditions constraining the ecology, reproduction, and stability through time of a species. It's basically something that you can quantify in a mathematical model and then project to space. Now, there have been instances, there have been already examples in the literature of the application of this ecological technique in deep time, and in the invertebrate realm, but also in the terrestrial one. Recently, a study on terrestrial turtles in the Cretaceous. And in order to do that, you need, of course, fossil occurrences which have a precise stratigraphical resolution. You need to know the conditions of the outcrop where you're modeling your occurrences and your envelopes, and you need a spatial homogeneity of data. So you need quite a few things in order to be able to create a reliable ecological model. So just for showing you an example of one of the application in deep time of this technique, you can, once you build a time slice a time-sliced projection of a habitat suitability in a particular stage of time, you can then do that for different time stages and then project the diversity trend based on the niche suitability through time. And you can show, for example, in this study, the demise of mammals in the last glacial maximum because of the increasing of temperatures. So it's something that you should take in mind from now on for the rest of my talk. So my dataset basically consists on paleogeographic maps made by GTEC. I decided to focus on North America because you've got nice time resolution. It's a better sampled area, topical for diversity trends in the late Cretaceous especially. And this historically has been more heavily sampled than other areas. Based on these models, based on these geographic models, and people in Bristol run paleoclimatic models to get some climatic outputs from these data. So we got, for example, temperature condition using boundary conditions for the Cretaceous. We got precipitation conditions, things that look like that. Now, we know that these climatic and geographic and tectonic parameters have also a severe effect into the distribution of taphonomical environments and the diagenetic environments suitable for fossilization. So we thought about using even this information to derive a spatial map where you've got a taphofascist map, where you've got the suitable environments for the preservation of fossils, and then use the isolated environment to match them with the rock records and highlight which are the areas that best preserve the best possible fossil record for a model and for the rock record, and then train our ecological models in these areas. So what I did was then taking every condition, every climatic condition or geographic conditions that can have an effect on fossilization process, and run some correlative statistical approach like chi-squares or Pearson correlations to highlight the areas that best would preserve fossils. So for example, you've got here, based on topography, a division of these spatial environments where you've got, of course, a nice taphonomical suitability in lower altitude environments. And we did the same for parameters like temperatures or precipitation, surface runoff, sediment flux. We use some basic drainage analysis to integrate precipitation patterns, tectonic, slope, and temperature to build which are the area which will provide the sediment flux suitable for fossilization. And taking into account all these data, we then built a mathematical model that includes this is a simplified version in this green area, all the conditions for every parameters that would provide a suitable fossilization area, and then projected that in space, matching with the rock record. So then we decided to select this isolated area to then build our model that would be projected at a regional or a global scale. We decided of using ceratopsid, hadrosaurids, and tyrannosaurids because they're functionally more homogeneous in every subclade of them. They're more represented in the terrestrial environment, the late Cretaceous of North America, and they're better sampled. So once you've done it, you have something like that. So we built that for every substages of the Campanian and the Maastrichtian, and you got something like that. You got an habitat suitability for, let's say, Centrosaurian in the Campanian. This is for hadrosaurians. This is for tyrannosaurids. And then you can do that for the Maastrichtian as well, and you can say how the habitat suitability from a stage to another can change. And you can go further then. You can now, once you train these models, when you know which are the conditions that would provide a suitable environment for these taxa, into an interval where you know there's been a biotic crisis, the Danian. So we use these models to project that into the Danian and see which is the theoretical abiotic biological trend. And you can see that you've got plenty of habitat suitability in the Danian for ceratopsids, for hadrosaurid, and for tyrannosaurids. So that must mean that there was an abiotic cause, a slow decline in abiotic cause that caused the demise of dinosaurs slowly on the lead up of the KPG. But you can also go further. You can build a time slice analysis and build these models where you show which is the trend of niche migration through time. So if you think about what these guys did with the mammoths, you can do something similar with these dinosaurs, and then you can show a diversity trend based on niche modeling on the lead up of the KBG. And as you can see, confirming what Carl showed before on the disparity analysis, you don't actually see a diversity trend decline from the companion to the mass restriction. You actually see an increase in abiotic diversity. And that also means that you've got plenty of niche space in the Danian, which would mean that you would go into some sort of explosive radiation to whichever taxon that would have all the abiotic niche freed from the extinction or of other dominant animals. And to show you some sort of additional prediction that I just recently added to this study that I'm writing on, last week or 2 weeks ago, Andrew Farke published this the first Ceratopsid evidence from Appalachia. As I mentioned before, it's an area which doesn't show really an abundant fossil record like it does at Laramedia. So he also theorized that this dispersal event must have happened at some time between the Maastrichtian and between the Campanian and the Maastrichtian, sorry. And with the aid of these models, you can actually timing the migration events. Because if you plot that with the niche modeling, you can reconstruct that these sort of migration must have happened between the late Campanian and early Maastrichtian, because you not only have the geographical suitability with an actual topographical bridge, but you also the suitable condition for this subtaxon to disperse between an area to another. So you can eventually build on these models and plot them to phylogenetic biogeography, for example, to better time up the timing and dispersal events for biogeography, for evolutionary biogeography. And once I build this sort of case study, my idea would be to match this sort of analysis with ecomorphological data, and then better refine the timing and dispersal events of biogeography and the microecological trend in extinction events and across time. Thank you very much. I would like to thank you all, the ProcPal organizers and my supervisors and the people from the Paleobiology Research Group. Thank you.